Hello. In this video walkthrough, we're going to look at this notebook, which talks about the calculus, the basic calculus for deep learning. Um, so it's very important to calculate the derivatives. And in this context, we're talking about the derivatives for vectors or tensors. Why is that important? Because in neural nets, essentially we're just doing very simple computations like weights times input plus a bias, and we get the output for the next layer, right? Um, but there is a loss function, which is the difference between the output and desired the desired uh, label or outcome, right? And we want to minimize that. Want to minimize the loss function. And the way to do that is to kind of through back propagation, and we do a gradient descent. And in order for the gradient descent to be efficient, we want to um, basically descend on the direction with the largest partial derivatives. So that is the motivation. Okay, so in the first section, we talk about some of the derivatives, the most common functions, the loss functions, and the activation functions, and the common forms of their derivatives, such as this. Yeah, so. This visualization, we can see, for example, sigmoid, ReLU. These are all activation functions. And in order for backpropagation to work, we have the chain rule, which sounds familiar if you've ever done basic algebra and the same rule works in tensor or vectors, right? That's the good news. So yeah, here we're just demonstrating that how chain rules work in the 2D and with partial derivatives, right? So in the next section, we'll talk about the partial derivatives and the gradients. Okay. So here it says a neural net has millions of parameters. Now, what does that mean? In vector space, that just means we have millions of axes, right? Dimensions. Each different parameter represent an axis or an uh, dimension. In textbook, we often see 2D or 3D vector spaces. Those are the common ones because we as a human can only understand up to three dimension vector space, right? Um, well, let's say in 3D dimension, we have three axes, meaning that we can go three directions. And a partial derivative means for a function or for a vector at that point, it's derivative with respect to each of the axes, each of the dimensions. So this is basically what this is talking about. The partial derivative is the derivative of a function f, treating everything except x as constant, right? So basically, we're taking the function, and for a given point, we're trying to find its derivative along a certain axis, XYZ axis, right? But only that's for a 3D dimension. When it comes to neural nets, we could have millions of dimensions, so the partial derivative is going to increase accordingly. And yes, so this is the motivation why it's important. So for the gradient descent to work, we need to find among all these partial derivatives, we need to find the one that's biggest. So when we go on that direction, we have the steepest slope. Yeah. So yeah, like we said, so this is the visualization of that. Um, and we essentially want to reach the lowest point. So imagine we start at any arbitrary point. We want to find the most efficient direction where we can get to the bottom, right? That's where the partial derivative comes into play. So yeah, the gradient descent, this is the key mechanism for neural networks to work, right? Uh, so we just keep going down, aka descent in this gradient map until we reach the valley, or reach the bottom. And this is actually just the loss function, right? We want to achieve minimum loss. That's the goal. So yeah, that's basically everything. Now that we have finished grading this, so we have gotten to the lowest point, right? Back propagation. So this is the last missing piece. We want to use like forward pass and backward pass to kind of readjust the weights, right? We have at each layer from the input to multiple hidden layers and to the final output layer, we start out with some randomized weight because we don't really know what's the optimized weight yet. In the previous step, we do gradient descent, right? We found for starting from the output, we found, okay, we go backward one step. We adjust the weights. And then we propagate that to the previous layer and we adjust the weights and so on and so forth. We do this multiple iterations until like the entire network, all the weights are optimized. So yeah. So with this, you have a working neural nets, and this is all the algorithms, sorry, all the algebra, the calculus behind it. All right, that's it. Thank you.